So we'll have now Mattia Marinelli. Thanks. I'll just put the USB. So that's our first in-present speaker. So that's great. Thanks for joining us. So yes, it should work. Now we try. So he has a background as an electrical engineer and a PhD in power systems from Italy, and he is now associated.
Electric vehicles, pure electric vehicles, not plug-in hybrid. In Denmark, it's 7% at the end of 2023, and just last month, we ended up with a 10% of the overall number of cars that is electric. So that's quite a good number. But other European countries are not, let's say, so well in the same situation. And it is still a kind of a subsidized market. So it of course depends a lot how the subsidies go in order to see whether the sales are proceeding or not. Now, moving forward, I think Daniel, you need to click on the screen, otherwise I lost
Because the microphone was not working, so I had to.
Sorry,
this was meant to be the presentation.
Yeah, that's not good. So I'll give you some insights of, let's say, my own setup that I have at home, which would be a kind of setup that you would have whenever you have the possibility to charge at home. So I have a 6 kilowatt photovoltaic system on my rooftop. I have 2 electric vehicles, one mine and one my wife's, and a charger. As a matter of fact, the one that you call a charger is not really a charger per se. It's just a glorified socket, as a matter of fact. The charger practically is on board of the car. So that device is just a controller practically. Then there is a meter and there is a utility meter. This is quite important because the utility meter is just there for billing purposes, but it doesn't really take part in the controlling action. So the utility meter doesn't transmit any information to actually realize any kind of smart charging control. It's actually these 3 devices. So the photovoltaic inverter, which actually comes with also a data logger that basically gathers the data from the point of connection, basically to the public grid, and then eventually sends information to the charger in order to say, now you can charge, how much power you can charge, and so forth. In terms of capability, the 2 cars come with different onboard charging capabilities. So specifically the Leaf as a one-phase charger, meaning that it can charge between 6 to 16 ampere one phase, while the Peugeot with kind of common with newer cars, come with a 3-phase onboard charger. So it can be 6 to 16 ampere, but times 3 because of the 3-phase. That practically translates in a power level that can be between 4 to 11 kilowatt. Now, some examples of how to handle the EV charging, because the base point, as you can imagine, is trying to charge much as possible with locally produced solar energy. That's the overall objective. And keep in mind, the current system, the photovoltaic system has no incentive whatsoever. So the only economic benefit that I have with the photovoltaic system is just to self-consume the local production, because what is paid by the grid, it's basically very, very little. So my incentive is basically to charge whenever there is sun available. Now, there are a few things to take into account. This is just to get an idea of what we are talking about in terms of kilometers. If you want to have a rule of thumb, 5 kilometers require 1 kilowatt hour of energy. And on average, the Danish driver drives 15,000 kilometers per year. So that would be 3 megawatt hour of electricity that you need to charge over a year. There are a few requirements, and they are basically all constraining the kind of problem. In that sense, you don't want to charge with a low power, too low power, because otherwise the efficiency sucks and you basically burn a lot of energy in the charge. You might not want to charge with unnecessarily high power, and that goes a little bit against your own interest, because from an efficiency and from a time point of view, the higher the power, the quicker the charge, and also the more efficient. But from a societal point of view, if everyone is charging at a very high power, then you are simply going to strain the grid. That means that you are going to force the utility to reinforce the grid, which has a societal cost that in the end will be just built in the electricity grid. You want to keep a certain level of energy, minimum energy, in order to ensure a minimum number of kilometers that you can drive. But at the same time, you don't want to charge unnecessarily too much energy, because as a rule of thumb, the higher is the state of charge, the faster is the degradation in the car. While the lower the state of charge, the longer the life is going to be in the car. And everything trying to do that whenever there is a sun shining, keeping in mind that if you need to use the car during the daytime, the car is not at home to charge when there is a photovoltaic production. So that, of course, creates some constraints on the way. This is just an example of efficiency curve for the two cars, where you can see that for the Leaf, that the one-phase charger, the efficiency gets down to 80% when you are at minimum power. The standard specifies 6 ampere. That's the minimum charging level that you can have. While, for instance, the Peugeot, the efficiency is decent whenever it's on a 3-phase level, but then when it switches for 1 phase, it gets very, very low. So this is something that you have to keep in mind, because low power might also mean simply more losses. These are some examples on some charging processes. Now, these days, you might not be familiar, but you recognize the production curve of a photovoltaic system during a summer day or during the nice days of the year. And this one would be, the yellow part would basically be the area that is charged by the car, covered by the sun. So in this case, there is a simple time-based control. So there is a clock that is basically saying, okay, start to charge the car at this point and finish at this point. And that's kind of, a little bit more than dumb charging. Otherwise, something that is a little bit more smart, you take advantage basically of the available power, and then you modulate the charging process. Again, in order to modulate the charging process, the charger needs to be informed on what's the available power at the point of common coupling. So what's the leftover production that is not needed by other appliances in the household. So in this case, you have a white, yellow curve here that is representing a heat pump, plus some dishwasher here or some washing machines here. And the purple one, it's basically what is left for the car to charge. And you can define different variation in the control strategy, where you say, if there is not enough power, stop the charge. So basically put it on hold, which is like the case down here. Now, these are just two examples. Over a summer day, clearly the situation is a little bit more challenging in, March, and you can imagine November and December, it's going to be clearly no fun at all. But in that case, you can see that also when you have more limited resources, then you need to be a little bit more careful on how you handle your resources. So in that sense, you can also set some charging over a night. For instance, if you charging during the night time, and I will explain a little bit better what's the point of charging between midnight and 6, and then you can use residual production during the daytime. Now, to give you some insight also from my own experience over the last 4 years, these are some statistics based on production point of view. So the 6 kilowatt practically produce 6 megawatt hour of production over a year. So it's 1,000 hours equivalent of production. Over the last few years, with the electric vehicle, I've been able to charge more or less 1.5 megawatt hour locally, entirely based on sun. This is practically covering 30% on a yearly basis for both cars, which is a decent number considering that the good months in Denmark are basically between March and September. Then you cannot really do that much around that. And then you can see here the number, the own consumption, which would basically be the metric that measures the amount of production that you can locally consume. It's pretty much half of what is generated. From the consumption point of view, this is the situation now. 2024 is not over yet, but practically the self-sufficiency, which is the complementary metric. So it's basically stating how much of my consumption I was able to cover locally. It's again around 50%. So that's a decent number. Now, moving a little bit forward and give you also some general insights, not just based on photovoltaics. How the setup works in Denmark is that whenever you are buying electricity, you are not paying just for the price of electricity, but you're also paying for additional cost. So the setup is basically that the retail price that one will consume is based on the spot price, which is of course a result of market. Depending if there is a lot of wind, how the interconnectors, if there is a lot of PV in the system. The price can be extremely volatile, can be negative in the situation that there is excess of demand and excess of generation, and then basically the generators pay to actually produce, to very high level whenever there is a scarcity or there are few renewables. So this is the varying part. And then there are some other fixed costs that there are different actors. So Energinet, so the transmission system operator, gets a small piece of the cake to operate the transmission system and to balance. The distribution grid operator gets a larger part of the cake. And what is interesting in Denmark is that quite, let's say, new compared to a lot of other countries, we have a varying tariff throughout the day. So the utility is charging different costs throughout the day, so that they disincentivize practically people from charging between 5 and 9 in the evening, which is the peak time, while at the same time they put a low premium between midnight and 6 in the night, so that everyone would be incentivized to charge there, where it's more statistically that the distribution grid would be unloaded. Then there is the retailer, which is the one that you basically buy the electricity from. In this case, they don't charge any fee because it's a subscription base. And then there is a state that is charging 2 fees. One is a, let's say, generic electricity fee, and another one is the VAT that everyone pays. So that is basically forming the price. In terms of electricity, just to give some insight, before, let's say, the pandemic, electricity prices were fairly low and also fairly constant throughout the day. So the variability between low and high prices was very, very limited. Everything changed. Of course, after the invasion of Ukraine, and 2022 experienced extremely high and volatile prices. And this kind of volatility, it's still there, even though the prices in absolute terms are more reduced. In Denmark specifically, wind is of course driving a lot the prices. There is a lot of wind, prices get down. There is less wind, prices get up. So that's a kind of rule of thumb if you don't want to have any sophisticated tool. Then this is an example, basically the same information as before, but just prompted as a chart where you see the breakdown of the costs between the fixed component. So the orange one would be the distribution grid component here. Then the transmission one is the yellow, the system is in blue, the energy fee is in green, and then the VAT. So you can see how the utility has been setting up this scheme so that they really disincentivize you from utilizing the energy between 5 and 9, because the utility is where it's actually experiencing most of the load there. And they have two varying schemes between, let's say, the winter period, so October, March, and the summer period, where they tend to punish less for that type of consumption. Because of that, we are also analyzing through our research project also behavior from other people. We have been analyzing actually. This is from 1,800 households in Denmark, all with home charging base. So this is not public charging based, but this is including both electric vehicles and also plug-in hybrid vehicles. As you can imagine, a plug-in hybrid vehicle has a smaller battery, and that means that the amount of energy that they charge every day, it's less compared to a battery electric vehicle. And what we are experiencing is that, as a matter of fact, there is this user response. So users tend to shift heavily the consumption between midnight and 6. And so far, this is fine. But at one point, when the number of cars will increase, this might not definitely be acceptable anymore for the utility. And this tariff-based approach, which is working fine now, will definitely not work anymore in a few years. So they need to come up with something smarter other than relying on that. But this is also, and also moving a little bit forward and towards the end of the presentation, this is also posing some interesting dilemma, because the utilities or the distribution system operator is, of course, assigning a price based on the loading of the grid. But this might not necessarily coincide with the CO2 content of the energy in the system. So as a matter of fact, this is looking at 2023 values. The CO2 content in Denmark, in the UK2 area, has, of course, a strong correlation with wind power, but it doesn't necessarily have a strong correlation with the evening peak. So in that sense, the utility trying to disincentivize the charging here and pushing the charging in the middle of the night might not necessarily fulfill the need to actually charge with energy that has a low CO2 content. And this is, of course, starting to become an interesting dilemma on where to put the boundary. This is just the same information as before, where you see the CO2 content in Denmark. This is a time series over here, and that it is extremely varying. And if I plotted the wind output, you would see a pretty strong negative correlation between wind and CO2 content, meaning that every time that there is a valley here, it's very likely that there is a lot of wind production in the system. Now, wrapping up, and I guess there might be some questions on bidirectional charging and vehicle to grid. Now, the setup that is described here, it's just relying on unidirectional charging. So smart charging, basically modulating the charging process, not really discharging into the grid. And whenever you hear bidirectional charging, you need to be specific. What do you mean? Because bidirectional charging implies charging and discharging. But the point is discharging for what purpose? There can be multiple purposes. Let's say optimizing your local consumption or speculating on the energy market, providing ancillary services. So there are at least a lot of varieties of different bidirectional charging. Some may be profitable, others are a little bit not profitable yet, at least. Just to give you a simple example, this one was, let's say, an extreme day back in January, when there was a huge variability of the electricity price throughout the day, with very low price at night and extremely high price in the evening. So in that sense, a bidirectional charging scheme could make sense also economically, by basically charging at night and then covering your own consumption in the evening, so saving a cost. Now, this is a day, and if all days were like that, that would make sense, but this is also a little bit of an outlier, so that shouldn't be taken as a representative. But in the future, that might come actually more frequent, so that might be interesting. So, summing it up, EVs are picking up, though with some ups and downs in the different markets. PV-based smart charging is definitely an effective way to decarbonize, also in Nordic countries, clearly with some limitations. The tariff-based scheme and variable pricing are definitely important tools to actually promote charging, but they are not definitely the silver bullet for the time being. And vehicle to grid, if you are in the sector, you have been hearing about vehicle to grid for the last 10 years. It didn't really pick up so far, but maybe now the time is coming back. I would say that's it, and I'm sorry for the extra time that I took, and I welcome any question. Thank you.
And thanks a lot. You can be sorry because it was our problem with the technical part.
No worry.
We have time for maybe one quick question, and then you can take the ones who are in presence can take a discussion more in depth, and the others online can just write it in the chat.
Yes, just a curiosity more than question. In your house, I didn't understand how much was the PV.
It's a 6 kilowatt.
6 kilowatt the PV.
Yeah.
So, the second question, you do not have a batteries, right?
No.
Okay, that's a problem.
But also with a battery, the battery might be 5 to 10 kilowatt hours. So you might use the battery more like to cover your local consumption. I wouldn't use the battery to actually buffer the PV production and then to charge the vehicle.
Well,
because of
when the prices are.
Yes, but not to charge it. So I would rather prefer to postpone the charging of the vehicle when the electricity is cheap at night, rather than using electricity from the photovoltaic to charge the battery and then discharge the battery to charge the vehicle. Conversion losses, unnecessary cycling of the stationary storage, and then you use the storage for that, and you don't use the storage to cover your own consumption during the day, the rest of the consumption.
Depends on the price.
It depends on the price. I agree. It's not black and white.
Last question. Show that there is a communication between the inverter and the charging station.
Yes. Yeah.
So the new hybrid inverter, the communication possibility. With
yes.
The
so
station.
I have to mention this is of course a solution that is coming from the manufacturer. This Fronius photovoltaic inverter, and the charger it's their own charger, so it's an embedded communication. Yeah. Yes. Anka.
Thank you very much. It was quite
A little louder.
Yeah. Yes. I just have a question. Does this controller consider negative prices?
You can definitely consider negative prices in case you want to charge by price and not charge by photovoltaics. So what I was showing here was more like you want to charge based on residual photovoltaic production, but you can also set the charging process to follow the electricity prices, and then you can put basically threshold. Yeah.
Then if you are sending the power there where it's negative price, so
yes, yeah. So in that sense, so your point is that it happened quite a lot during the weekend this year that Sunday and Saturday it was negative price throughout the day, so the photovoltaic production I had to pay instead of being paid. So in that sense, the point was to charge the vehicle. But in that sense, the approach is always power-based, because in the end, what you want to minimize is the photovoltaic power that you send into the grid, and that would basically save the penalty for paying. Yeah, so it comes in kind of implicit. Yeah.
Okay. Oh, thank you very much.
Sure. Thanks.
And when you look upon it, without solar, you never have this. Never negative prices are not exempt because you have always to pay diesel. So if you don't have solar and you charge a car, even if the price negative, you have to pay the diesel for it.
It depends how negative that
And sorry, we take this during the discussion later, maybe because otherwise our next speaker might get angry.